All right, what's going on, guys? We're going back to 2D. I'm not sure why the book did that. It was problem 332 was a symmetrical 2D problem. Then it went into 3D for some reason. Now it came back to 2D symmetrical problems. But you know what? This one, we have to use symmetry to determine displacements at the nodes and then the stresses in each element. They give us modulus of elasticity. They give us the areas, cross-sectional areas, and they give us lengths in feet. So just keep a lookout for that. But you know what? Let's go ahead and get started. All right, guys, so for these problems, right, we're going back to 2D. This is our stiffness matrix for a 2D problem in the X and Y direction. We got cosine values and sine values. We square them. We know E, A, L. Well, we should know L, right? They give us 6 feet, but we're trying to keep everything in pounds and inches. So we're going to have to convert this. Let's go ahead and do that right now. If you do that, L1, which is this element right here, that's going to be, this is a 3, 4, 5 triangle, right? 3, 4, 5. Just that 3 became a 6, that 4 became a 2, so that means L1 is 10 feet. If you convert that to inches, that's 120. So for L2, let me put inches right here. L2, which is this one right here, that's 8 times 12. That's going to give you 96 inches. And L3 is this one right here. That's going to be 6 times 12, which is going to be 72 inches. Now, this is a symmetry problem, so we're going to have to cut this figure in half. And obviously, you want to do it on the vertical axis, right, to make it a perfect, even symmetry. So that's what we have right here, okay? And when you do that, there's one important assumption that happens. But first, let's just take care of this one right here. That's a circle. I think this was a roller, right? There we go, a roller. So you could move in the positive x direction or negative x direction, but you can't go up and down. It's kind of fixed in that sense. So that means one boundary condition is going to be V1, right? Y displacement at node 1 is 0. So just keep that in mind, okay? What else? What was I doing? Oh yeah, we did the symmetry. And there's the other important assumption. So when you cut it in half, you're assuming there's going to be no translation in the, the x direction on both of these nodes. And it's kind of true. If you saw some of my other videos, when you do that, you get a really small displacement. I think it's like 1/3 of a millimeter. So just think about how small that is. So yeah, this is the assumption you have to know how to make. So when you cut it in half, you get rollers right down the middle, okay? Just remember that. If you remember that, you'll be on the right track. What else happens? So when you cut it in half, this beam right here has a cross-sectional area, right? Imagine it's a tube, but since you cut it in half, that area gets cut in half. So it's area of 3 to 2, or 2 to 3, whatever you want to call it, gets cut in half. And then the force also gets cut in half. So 20,000, so let's just put force at 2 gets cut in half as well. So that's, if you don't do this, it's going to mess up your problem, and you'll see it. There's a way you can verify it. I'll show you at the very end, but just keep that in mind, okay? Let me see what else. Oh yeah, these are, boundary conditions as well, right? They're preventing translation in the x direction at both of them. So that means this is U, right? U3 is 0, and that means U2 is 0. So it's going to help us out a lot because it's less variables we have to deal with, right? And yeah, I think that's pretty much it. That's the most important part of this problem, knowing how to set that up. If you know how to do this, you'll be all right. They try to trick us with the feet, okay? Just keep a lookout on that. You want pounds and inches in this case because you want PSIs, you're going to get stresses and you want it in PSIs. But let's go ahead and just start filling in this table, right? This is step 1. Don't worry, I'll cover. I've been doing it right, but just there's a lot of stuff here written, but I'm gonna cover that up. So step 1, right? We want to fill in this table. Now, the reason we need to do this is because we want to fill in the stiffness matrix, right? We want the cosine squares, the sine squares, but you can't do that without getting the cosine and the sine. And you'll also need the cosine and sine for stresses, but that's later. Just till we get there. So the first element, right? It's this one right here. Now you get the angle. So me personally, I like to go from smallest node to biggest node. So 1 to 3, okay? So I'm gonna make that node right here, 1 to 3. On the second element, I'm gonna go from 1 to 2, 1 to 2, and then from the third element, I'm gonna go from 2 to 3. Now you could go the opposite direction, 3 to 1, 2 to 1, 3 to 2. But I just like to be consistent because when you start filling in this matrix, it can get a little complicated. It's easy to get confused. I just like to go from smallest to biggest. So that's what I suggest, but it's up to you. I'll show you how to get the angle for both. So we're going from 1 to 3, right? This is a 3, 4, 5 triangle. So that means this theta right here, that is 36.87. That's just trigonometry, right? You could use tangent, sine, cosine. You know the lengths. You could get that angle. You could get this one too, okay? So this angle right here is 36.87. And so that's the one I'm gonna use, right? Because I'm putting my axis at node 1. So the positive y, positive x. This beam goes up this angle right here. So that's why I'm using 36.87. Now, let me show you if you would have done it from 3 to 1. The angle you would have used, if you went from 3 to 1, this would have been your positive xy. This is your x, y. The angle you would have used is 180 plus this angle right here, which is also 36.87, right? You know from trigonometry that this angle is the same as this angle. I forgot what it was called, like congruent or like, I don't know, right? Supplementary, some shit like that. But point is, you would have used 180 plus 36.87, which, let me just do it real quick. 36.87, you would have used 216.87. Okay, just FYI, that's how you would have done it if you went from 3 to 1. And I'll show you how that would have changed here in the matrix, but just FYI, that's how you determine the angles. I like to go from smallest to biggest and just use that. In this case, we went up 36.87 degrees right here. If you get the cosine and sine of that, you'll get 0.8. You'll get 0.6 for sine. Square cosine, you'll get 0.64. Square sine, you'll get 0.36. Cosine times sine is 0.48. And we'll fix that up later, the EA over L. Now the next one, from 1 to 2, that angle 0, right? It lands right on the x-axis in our case. Because we're starting the axis right here at the smallest node. And relative to that axis, that's 0 degrees. And if you get the cosine sines, you will get 1, 0, 1, 0, 0. Okay, that's just trigonometry. Finally, from 2 to 3, we went up 90 degrees. Okay, if you would have went from 3 to 2, you would have used 270 degrees. Okay, because you went all around. And then for this one, I didn't mention it, but if you went from 2 to 1, you would have used 180. Okay, but that's pretty much the trick. It's nothing too crazy. I'm pretty sure teachers don't explain that. I had to figure that out on my own, I remember. But that is the trick. Okay, just whatever node you start at, and I like to go from smallest to biggest. Just get that angle. That's all it is. Now let's get EA over L. So all the EA over L's, they're gonna be normal. So let me explain. So for the first one, first element, right? They give us the E, and they give us elements 1, 2, 4, and 5. So 1, 2, 4, and 5 have area of 10 inches squared. Okay. Element 3 has 20, so this bar is twice as thick as the rest. Okay. So we're gonna get these normally. They already give it to us. EA over L, right? So it's 30 times 10 to the 6 for the first element times 10 divided by 120. Now, if you do that, you will get 25 times 10 to the 5th. I had to move the decimal, just FYI, that's how I got. So it's 300 divided by 120, that's 2.5. And then I just moved the decimal over to get 10 to the 5th, not 10 to the 6th. And then element 2, just, again, normal. The only one that's not going to be normal, I'm going to go ahead and give you this number. The only one that is not normal is the one you cut in half. You got to take that into account, remember? But fortunately, I mean, 20 divided by 2 is 10. So I guess it's just 30 times 10 to the 6 times 10 divided by length. And the length changes for each one, remember, okay? So it's not always 120. It's, for this one was 96, and this one's going to be 72. So this one's going to give you 41.67 times 10 to the 5th. All right, so that means we could go ahead and start filling in the tables, right? Stiffness 1, we already have EA over L. We already have the cosine squared, sine squareds, and cosine sines. First element, right? We are gonna go ahead and do stiffness, which is of element 1. It's 25 times 10 to the 5th. So I'm gonna put 25 times 10 to the 5th, and it goes from 1 to 3. So you're gonna put U1, V1, U3, V3. Now, if you would have done from 3 to 1, you would have put U3, V3, U1, V1. Now, doing that, I'm gonna go ahead and whatever. I'll just, hopefully you could see it, okay? U3, V3. That's V1 right here. So, what was I saying? Yeah, that's right. Normally, it's not going to change. It's not going to mess up your global stiffness matrix, but when you start looking for stresses, that's when it's going to screw you up. So, you'll get this part right. And if you only ask for the global stiffness matrix, I guess you dodged a bullet. But once you start looking for stresses or forces, you're screwed. Okay? So, just be consistent. U1, V1, U3, V3, because we chose that order. Now, let's go ahead and do K2, right? K2 is 31.25 times 10 to the 5th, okay? And that goes from 1 to 2, so it's U1, V1, U2, V2. Same thing here, U1, V1, U2, V2. Finally, for element 3, right, 41.67 is our stiffness, so 41.67 times 10 to the 5th, and that goes from 2 to 3. So U2, V2, U3, V3. Same thing going this way, U2, V2, U3, V3. All right, now before we start filling in the table, you could do it. I mean, this one's a little 4x4. It's not that bad compared to 3D. But let's go ahead and start applying the boundary conditions first, okay? So we know V1 is 0, U3 is 0, and U2 is 0, okay? So V1 is 0, so this gets canceled out. And this way too. What else? U3 is 0, which is this one right here. Okay, so that gets canceled out. Up and down and side to side, not just up and down, right? U2 and U3 in this case. So right here. It's really easy to get confused. I think when I was doing the problem, I got confused. So just make sure you're crossing out the right ones. And then in this one, only V1 and U2. So V1, U2. And again, it's because they're 0. That's why we're doing this. It's a boundary condition, so we can do it. Okay, and I think that's it. Yep. Yeah, I don't think I missed one. So I think we're good. So we're going to use this matrix outline. So it's symmetrical, right? So that means CS goes here, that negative C squared goes here, and that negative CS goes here at the corner. Negative CS goes here, negative S squared goes here, and then CS goes here. It's just symmetrical. Okay, so we're going to start filling that in. The first U1 position, that's C squared. For element 1, that's 0.64. For element 1, these two got canceled out, so we're going here. That's S squared, right? This position right here is S squared. So we're going to get that 0.36. Okay, 0.36. This top one is negative CS, so that means this one's also negative CS. And that CS is 0.48, but it's negative, so we negative it, or whatever you call it, 0.48, and that one's done. Okay, let's go to the next one, K2. Same positions, C squared, S squared, negative CS, negative CS. So it's 1, I'm looking at these 1, 0, 0. So it's 1, 0, 0, 0. Well, that one's easy. And then finally this one position is S squared, right? This one right here. Then we got negative S squared, negative S squared. Cool, so that's 1, 1, negative 1, negative 1 for element 3, okay? 0, 1, 0 now. And that S squared was 1. So it just became positive, positive, negative, negative. And yeah, we should be good. Now, before we start moving on to the global stiffness matrix, to get here, you got to add these matrices up. Now, you cannot do that unless they share the same common multiple outside the matrix. In this case, they all share 10 to the 5th, so that's cool. But they don't share, like this one is 25 times this. This one is 41.67 times this. This one's 31.25 times all of this. So what we got to do is we got to throw that in there. So 31.25 times everything inside here. That's going to give you just 31.25. That was a 1, remember? So 1 times this is just this. So that means this one goes away. And the rest are zeros, so we're good on that. So that's just 10 to the 5th outside. Cool. That's what we want, right? Then what else? 41.67 times all of these. This is going to be 41.67. 41.67. Damn it. Gotta get rid of that negative. 41, and then this one too. And yeah, that means this one's also good to go. So doing the boundary conditions first saves you a lot of trouble. Just you see, we don't have to fill in the whole matrix for each one. Cool. Now it goes away, right? Because we already multiplied it in. So that's 10 to the 5th. This one right here now, 25 times all of these. If you do that, you're gonna get, what do we get? Hold on, give me a second. I already have the numbers, just erasing. But I hope you're following. It's not that crazy. It's just a process. If you can get the process down, you'll be all right. So it's -12 and 9. Okay, so that's what you get if you multiply 25 to the inside. And now we could add them up because they all share 10 to the 5th outside. That means you can add them up. Now, before we do that, we could go ahead and start doing the boundary conditions again to the global stiffness matrix. This is your global equation, right? You got your force vector, global stiffness matrix, displacement vector. Let's go ahead and apply the boundary conditions. V1 is 0. U3 and U2 are 0. U3, there we go. And same across, right? V1, U2, and U3 are all gone. They're not the straightest lines, but they'll work for now, okay? All right, so we go ahead and start adding all the positions at U1, right? Because we want to fill this one in, so it's 16, U1, right? 31.25, and that's it. So if you do that, you will get 47.25. Next one, U1, V3. U1, V3, there's one right here, and that's it. -12. Does U1 ever share a V4? Nope. Well, actually, what? Why did I do a V4? Ah, you gotta be kidding me. Hold on. All right, there we go. I must have gotten confused with 348 because there's 4 in the other problem. But I just want to go ahead and fix that, right? There's no 4 nodes. There's only 3 in our case. And yeah, so we go ahead and continue. Oh, I missed this one. U1, V2. U1, V2 is 0 right here, and that's it. Just 0 right there. And then, so here's a trick before we continue. It's going to be symmetrical. If you did everything right, it's going to be symmetrical. That's what I've noticed. Now, I'm going to go ahead and do all of them, but just FYI, it should come out symmetrical. That's a good way to check that you're doing it correctly. And you'll see what I mean right now. So V2, U1. V2, U1, there's one right here, 0. And that's it, right? There's no other one. V2, V2. So V2 pops up here. That's 41.67, and it pops up here, 0. So if you add that up, right, it's 41.67. All right. What else? Next one, V2 and V3. So there's one right here, and that's the only one. Yep, it is. -41.67. Next one here, V3, U1. V3, U1. There's a -12 right here. There's nothing here. Nothing here. You're starting to see the symmetrical, right? 0, 0, -12, -12. Okay. This one should be -41.67. Let's see. V3, V2. There's one right here. -41.67. Nothing here. Nothing here. Yep. It's working out. Well, it worked out actually. And this one is V3, V3. There's a 9 right here and a 41.67. There's nothing here. That's going to give you 50.67. Now let's go ahead and apply the boundary conditions, right? V1, U3, and U2 are 0. So these 2 are 0 and this one. So it's 0, 0, and 0. And if you know force, you don't know displacement, and if you know displacement, you don't know force. So that means since we don't know displacement at u1, we should know the force. If we don't know displacement at v2, we should know the force in the y direction, and at v3. That's kind of the trick to that too. It's a little hack I've noticed. But if you do that, at node 1 in the x direction, there's nothing being applied to it. Like in this case, right, we have 20,000 applied at 2. There's nothing in the x direction at 1, so that's 0. In the y direction at 2, it's 20,000, but remember, we cut it in half. You got to remember that. That's going to mess you up. Negative 10,000. And again, there's a way to verify your answer at the end. I'll show you in a bit. Negative 10,000. At least for this specific problem, or something that's going along your beam, not at an angle, okay? And then F3Y, there's nothing being applied in the y direction, like physically. You can't see it. So that's 0. And yeah, so that means we could go ahead and start assembling the equations. So the first equation is going to be, oh, forgot 10 to the 5th right here, remember, 10 to the 5th, right? They all share 10 to the 5th. Fortunately, it didn't mess us up. Now, you know what I'm going to do before I start doing the equations, actually? That 10 to the 5th, I'm going to get rid of it. I'm going to divide both sides of the equation by 10 to the 5th, and if you do that, all this remains unchanged. This is what's important. 0 divided by 10 to the 5th is 0. Negative 10,000 divided by 10 to the 5th, that's gonna be, I think it was like 0.01, and it's negative, okay? Negative 0.0. Actually, how much was it? Messed up. It's 10,000 divided by 10 to the 5th, 0.1. 0.1. Wow. Very small, very small. 0.1. Cool. So that means this goes away. And that just gives us one less headache to deal with, right? So start assembling the first equation. 0 is equal to 47.25 u1 plus 0 v2 minus 12 v3. Okay, that's the first equation. Next equation, that's gonna be negative 0.1 is equal to 0 u1, 41.67 u2, v2, I'm sorry, v2 minus 41.67 v3. And finally, the last equation, 0 is equal to negative 12 u1 minus 41.67 v2 plus 50.67 v3. Now, this is what I'm gonna do. I got 3 equations, 3 unknowns, right? There's the first equation, second, let me move up the paper in case you can't see, and third. Okay? Now, what I'm gonna do, look, I'm not gonna stay away from the third equation because that's the most unknowns, but look, if I get u1 in terms of v3 and v2 in terms of v3, I already got this in v3, so I could plug in u1 and v2, and I'll have everything in terms of v3, and I could solve for v3. So if I do that, right, equation 1 is gonna give us u1, if you do the math, u1 is equal to 0.254 v3. And equation 2 is going to give us v2 is equal to v3 minus 0.0024. Okay? And yeah, we should be good. So these two relationships are going to help us plug in to equation number 3, and then we get v3. So step 6, just real quick, it's going to be from equation 3, 0 is equal to negative 12 u1, but u1 is 0.254 v3 minus 41.67 v2, but v2 is v3 minus 0.0024, and then finally plus 50.67 v3, and that's it, right? That's equation 3. Now if you do the math, you will get 0 is equal to 5.952 V3 plus 0.1. And then if you solve for V3, that's gonna, you know what? V3 is gonna give you, let me make more space in case I need it. V3 is equal to negative 0.0168 inches. If you plug in V3 into this equation, you get V2. So V2 is going to be negative 0.0192 inches. Plug in V2 or V3 back into the first equation. U1 is equal to 0.254 V3. You'll get U1 is equal to negative 0.00427 inches. And that's your answer for displacements, at least. Now we're going to go ahead and find the stresses in each element. So the stresses in each element are, let's go ahead and do that. What step is this? We are on step 7. So let me move the calculator. Step 7. Stress for 2D elements is equal to E over L, negative cosine, negative sine, cosine, sine, and then the displacement vector. So it's U1 initial, or V initial, U final, V final. So initial and final, it's pretty simple, right? It's initial, final, initial, final, initial, final. 1 to 3, 1 to 2, 2 to 3 for each element. So that means for stress 1, it's going to be E over L. If you do the math, right, just E divided by its length. It's 30 divided by 120, and then times 10 to the 6. So that is going to be 25 times 10 to the 4. Is that right? Let's go. Let me go ahead and do that real quick. 30 divided by 120. Yes, it is 0.25, but then you move it 10 to the 4th, and then you get the cosine and sine values. So for element 1, cosine and sine was 0.8 and 0.6, but the first ones are negative, so it's negative 0.8, negative 0.6, then 0.8, 0.6, and then displacement vector U1 V1. So U1 was right here, negative 0.00427. That's the one we found, negative 0.00427. V1 was 0 is our boundary condition. U2 was 0 is our boundary condition, and V2, I'm sorry, we found was 0.0168, a negative. And yeah, that means we can go ahead and solve this one real quick. Let me move the calculator again. It is 25 times 10 to the 4th, which is negative 0.8 times the first one. That's going to give you 0.003416 plus negative 0.6 times 0 plus 0.8 times 0 plus 0.6 times this number. And that's going to give you negative 0.01008. Now sigma 1, which is also the same as sigma 1 to 3, right? Nodes 1 to 3. This is element 1, this is nodes 1 to 3, which is also equal sigma from 4 to 3. So if you look at 4 to 3, because ours is 1 to 3, so symmetrical 4 to 3 as well. That value is going to be, what is it? Negative 1666 PSI. And since it's negative, that means it's in compression. That's the first answer. Okay. All right, next one. Sigma 2 is going to be equal to E over L. If you do the math, I'm not going to do it this time, but it's 31.25 times 10 to the 4th. Get the cosine and sines for element 2 now. It's 1 and 0, but the first ones are negative, so it's negative 1. Remember the formula, negative, negative. It's negative 1, 0, positive 1, 0. And that goes, this element goes from what nodes? 1 to 2. Actually, hold on. This one was U3, V3, I'm sorry. Okay? Yeah. It was U3 V3. It was I think I said 2. U3 V3. But I mean, the numbers are correct. I think I just said it wrong because I'm just following my other paper here. But yeah, it was from nodes 1 to 3, so U3 V3, and this is U1 V1. Now this one goes from 1 to 2, so it's negative 0.00427 and 0. And then U2 V2, which was 0, and what was U2? Oh, V2, I'm sorry. 0.0192 negative, so it's negative 0.0192. If you do that math, let's see, you will get 31.25 times 10 to the 4th. You only care about this one, right? Negative 1 times this, 0.00427, because 0 times 0, 1 times 0, 0 times this. That means sigma 2 is the same as, well, it's equal to sigma from nodes 1 to 2, which is also sigma from nodes 4 to 2. And that number, if you do the math, it's going to be 1333 psi, and that is in tension, positive. Let's see, let's go to the third one, finally. Sigma 3 is equal to E over L, right? 41.67 times 10 to the 4th, multiplied to the cosine and sine values, 0, 1. So that means it's going to be 0, negative 1, 0, 1. And then multiplied by the displacement vector. It's from nodes 2 to 3. So it's going to be U2, which is 0, V2, which was negative 0.0192, and then U3 V3, 0, then negative 0.0168. Okay, so if you do the math, 41.67 times 10 to the 4th, open parentheses, 0 times 0, negative 1 times this, 0 times 0, 1 times this. So that's going to be 0.0192 minus 0.0168. And sigma 3 is equal to sigma from 2 to 3, and that's it because it's the other side is the same bar, right? Symmetric. So it's 1,000 psi. Now you really can't verify your answers with the other, what do you call it, stress values, but you could do it with this one. This is what I was talking about. It's 1,000 psi stress, right? You know, force over area is equal to stress. Now, since it's being applied along the axial direction, that means 20,000 divided by the cross-sectional area is going to give you exactly that. And that's 20,000 divided by 20, that is 1,000 psi. So that makes sense. You really can't do it with these, right? Again, it's a little bit more complicated, but at least if you can verify that, you'll be all right. So that's the problem, right? There's the top, that's the bottom, and then this right here. Now, the only thing you should take away, well, a lot of things you should take away, right? But the biggest thing is dividing up your area and accounting for that here. Your force, dividing that and accounting for it over here. Remember, it was negative 10,000. If you don't do that, that will mess up your numbers. It messed me up on 348. I'm gonna do that one right next, but just letting you know, if you can do that, you'll be all right.